Hello everyone and thank you for being here today. Our Team 1 will present you our task 1 and task 2 of second assignment. And for task 1, we implemented a doubly linked list from scratch. Uh, the main difference between this and the normal single linked list, that every node here has two arrows instead of one. It points to the next node, but it also points back to the previous one. This is super useful because it means we can walk through our data in both directions, forward and backward, without getting stuck. Here's our source code of task 1. So let's start. To build this, we started with a structure called node. Inside we have an integer for the actual value, the pref pointer to go backward, and next pointer to go forward. We also use the type def node pointer named linked list. This just keeps our main code looking tidy, so we don't have to keep typing this everywhere. First here we made a quick function called the isEmpty that just checks if the list is completely empty by looking to see if the head is null. Then we wrote insert node here to add new data to the very front of the list. We grab memory dynamically using malloc check to make sure the system didn't run out of memory. It's our tree, and fill it with our value. Since we are always inserting at the front, we hook up the new node's next pointer to the old head. If there is already a node there, we make sure its previous pointer points back to our new node. Finally, here we update the head of the list. To get the output in the exact order requested, like 10, 20, 30, our function passes the numbers to this insert function in reverse. So it's 30, 20, and 10. Next is for printing and searching. We just do a standard loop through the list, standard while loops. Since we are only reading the data and not adding anything new here, we don't need malloc. For display lists, we print out the arrows exactly how the sample output wants it, showing the null bounds at the both ends. And for the for the find node for searching, our find node function walks through the list node by node, keeps count of the position, and tells the user exactly where the number is. If it reaches the end and finds nothing, it prints out not found in the list. Here the trickiest parts, delation. In delation, when you delete a node in a doubly linked list, you have to bypass it by stitching its neighbors together. If we are deleting the very first node, we just slide the head forward. But if it's in the middle or the end, we make the previous node point forward to the next one, and the next node points backward to the previous one. Once the node is completely unlinked, we call free to give that memory back to the computer, so we don't cause any memory leaks. We also threw free list function at the very end of main to clean up everything before the program completely closes. And here's our output. To wrap things up, to sum things up, we test the code against some specific edge cases in our assignment. First, as you can see from our test run, here the linked list is empty. It correctly shows that that list is initially empty with is empty operation, is empty function. Then we input three numbers, 30, 20, and 10, and it correctly shows after insertion that linked list is 10 in a up, in a head, and 30 in a tail. So after it, we go through some operations with find node function. 20 is like shows that value of 20 found at position 2. Then we do it with 50 that is not in the list, so it shows correctly about it. Then we delete node function. We use delete node function, and when we delete 10, for example, it correctly removes 10, and right now 20 is a head. After it, we delete 30 here, and it means that 20 is a head and a tail at the same time. After it, we delete 45. It's nothing changed. 20, we delete 20, and after it, the list is now empty. And after it, it goes through like last operation here because it's like remove all unnecessary traversals. And here, after we input 10, it say like the linked list is empty, and then process returned 0. That's all of us for task 1. Let us move to task 2.
Hi, my name is Yesemek Ali Khan. My student ID is CST2509113, and today I'm going to walk you through the assignment 2, which covers this task built by using single linked list. I'll explain you the program for the second task, how it works, and the logic behind each function, and how I handle different situations. Here is our source code. Let's begin. Why a linked list for a stack? A stack follows the LIFO principle when the last in and first is out, which means the last element you add is the first one you take out, just like a stack of plates. Here, the node top equals to none now means that the single pointer is the entire stack. When it is now, the stack is empty. I chose to implement the stack using a single linked list instead of an array because a linked list is dynamic and it does not need a fixed size declared upfront. You can keep pushing elements as long as there is a memory available, and each node is allocated individually using a malloc node, like here. Every time we push, a brand new node is created here in a memory runtime, which an array-based stack, you would have a hard limit on how many elements you can store. So here is the result. 342 was pushed last, so it is at the top. 556 was pushed first, so it sits at the bottom. Here I use the type def function to define the node structure. Highlighting this, each node has two things. Data stores the integer value, and the next is the pointer that links it to the node below in the stack. The type def means I can write a node instead of a struct node everywhere, which keeps the code clean. And the previous node top equals to null. I declared a global pointer called the top that starts as null, meaning the stack is empty at the start. Here, the add function pushes a new integer on the top of the stack. It returns an integer 1 for success and 0 for the failure, instead of void, which means the caller can check whether the push actually worked. Here, first malloc allocates memory for a brand new node, the size of exactly size of node, just enough for the one node. Then, here, I always check if a malloc returned null. If it did, memory allocation failed, so I print an error and return 0 to tell the caller that it did not work. Then, at the new code data value, then I store the user's value inside the new node's data field. Here, this is the K line. I make the new node point to whatever was previously the top, so the new node links down to the old top. Finally, top equals to new node means that I move top up to the point to the new node. It is now new top of the stack. Here is the before and after. 342 is now the new top. Everything else is moved down one level. Here, the withdraw function removes and returns the top element of the stack. It also returns an integer, not void, so the caller receives an actual value that was removed. Before removing anything, I check whether the top is null. If it is the stack and empty and there is nothing to remove, this is the stack under full condition, and I print an under full error message and return it immediately. If the stack is not empty, so I save a pointer to the current top node in a variable called temp. And I also save the data value. Then I move top down to the next node in the list. Then I call free on the tab to release the memory on the removed node. Finally, I return the saved value. Here is the before and after the withdraw function. The return value now is the 342. The display function prints all elements in the stack from top to the bottom. It returns an integer which is the count of elements printed, so the caller knows how many items were displayed. Here, if the stack is empty, it prints a clear message instead of a crashing. Then node temp equals to top. I use a temp pointer for transversal. I never move top itself because if I move top, I would permanently lose all the elements below. Then at the while loop, the loop runs as long as temp is not null, which iteration prints the data value and moves temp to the next node. This goes from the top all the way down to the bottom of the stack. Finally, the function returns the number of elements it printed, which caller can use if needed. Here, the counting function counts how many nodes are in the stack. Again, I use the node temp top, so the top stays untouched. Every node I visit adds 1 to the counter. Here, when the temp reaches null, the loop ends and the counter holds the total. The count is printed and also returned as an integer, so the caller has the value if needed. The stack underflow happens when you try to withdraw from an empty stack. Here the case 2. I check if the top is null before calling a withdraw function, which means the underflow check happens in the main before the function is even called. And this is even cleaner and safer because withdraw never runs on the empty stack. Here the menu uses a do-while loop, so it always shows the menu at least once and keeps running until user selects option 4. The loop condition is that always the bottom choice not equal to 4. And each cycle shows the menu, reads input and executes the matching case. For invalid menu choices, I added a range check before the switch statement if the user taps 0 to 9 or 1 to 4, which blocks catches it, prints an error, and continuous keyword jumps straight back to the top of the loop, so the menu appears again. For the input validation, I wrote a function called getValidInt. At the scanf, scan returns 1 when it successfully reads an integer. If it returns anything else, the input is failed. At the while loop, the loop clears out everything left in the input buffer, so the leftover ABC characters, so they do not interfere with the next read. To while, the outer loop keeps asking until the valid integer input is received, and after the reading the menu choices, it also checks that it is between 1 and 4. If the outside of the range, it prints out an error and skips the next to the loop iteration and reshows the menu. So before the program exits, I release all the remaining memory using the freeAll function. Here, at the while loop, this pops and frees all remaining node one by one until top is null. And it counts how many were freed and returns the number. This ensures no memory leaks when the program ends and the number of freed nodes is printed, so you can verify cleanup happened. So looking at the sample output, the user selects 1 to add 556. The stack shows 556. Then 444 is added since it goes to the top. The stack shows 445, 556. Then 223 is added and the stack shows 223, 445, 556, and 223 is now at the top. Then the user selects option 2 to withdraw. 223 is removed because it was the last one pushed because of the LIFO, and the stack shows 445, 556. Then when the user selects 3 for the stack count, the program shows there are 2 items. 2 items at the 445, 556, and then 342 is now pushed again, making the stack 342, 445, 556, and the stack now counts to the 3. Then when the user selects the option 4, the program exits and all remaining nodes for 342, 445, and 556 are freed using the free all function. And the program terminates. Here, there is an invalid inputs that were validated through the input validation function, which was the words using the text and the signs.
To summarize, this assignment taught us a lot about how dynamic data structures works in C programming. For the double linked list, the key thing we learned is that managing pointers in both directions requires careful handling, especially when deleting nodes. You have to update both the previous node's next pointer and the next node's previous pointer to keep the list consistent. And for the stack, we learned how natural a single list fits the LIFO, last in, first out behavior. Inserting and removing from the head is both simple and efficient, and it avoids a fixed size limitation of an array. The biggest challenge we faced was handling edge cases, especially single node deletion in the double linked list, and making sure the stack never crashes when it's empty. We solved this by always checking conditions before performing operation and by writing separate validation logic to handle each situation cleanly and clearly. Overall, this assignment gave us a much better understanding of how memory allocation, pointer manipulation, and data structures work together in C. So, thank you.
Finally, moving to the brief explanation on the challenges. The biggest challenges on the task 1 and the heading on the pointer update when the deleted node from the doubly linked list because of the each node as both a next and the previous pointer. So we had to think carefully about which pointer to update depending on whether the node was at the head, at the tail, or somewhere in the middle. So we solved this by breaking the deletion into 3 separate cases, which handles each one individually, which made the logic much cleaner and easier to follow. For the task 2, the main challenge was making sure the program never crashes when the user does something unexpected, like withdrawing from the empty stack or typing letters instead of numbers. We solved this with the underflow problem by checking if the top null is before calling withdraw function, so the function never runs on empty stack. I think for invalid input, we wrote the get valid input valid function, which uses the scanf and clears the input buffer if the read fails, then keeps asking until the user gives a proper integer. Overall, both challenges came down to the same lesson. Always validate before you act and always think about what happens when something goes wrong, not just when everything goes right. Thank you.